Hello everyone, we're starting chapter 25 today, and this will be the first of three chapters related to circuits. And so what I've done is I've just written out a couple of definitions here to save us a little bit of time when it comes to capacitors. And a capacitor is going to be any set of isolated conductors. So basically two conducting surfaces that do not physically touch, and regardless of the shape of these conductors, we're going to refer to those surfaces as plates. And when there is a difference of charge between those surfaces, there will be an electric field that is produced. So what we're going to do, just for the sake of simplicity, is we're actually going to produce two equal-sized parallel plates to help us set up the most basic of capacitor definition. And I didn't quite draw that the same size. So there we go. That looks a little bit better. So we have two conducting materials. They're separated by a distance. And what we want to do is we want to put some charge on either conductor. So we'll go ahead and put some positive charge on this top plate. Again, the shape does not matter. Right now it looks like we have a bar, but we could very well be looking at the edge of a circular plate. It could be an oval, square, rectangular plate. We really don't know at this point, but as we said, for the sake of simplicity, we'll just go ahead and assume that these are two flat plates of equal shape, and then we can start talking about how things will change if we start changing the shapes or the surface areas of those conductors. And so on the bottom plate, we need a different charge, and the easiest way to do that would just be to put some negative charge on that bottom plate. And as a result of all of this, we're going to see electric field lines form between the two plates. And between these two plates, the electric field will be pretty uniform because of the whole evil twin scenario of electric field lines intersecting and canceling out their horizontal components. So we'll go ahead and assume that we have a uniform electric field between the plates. Outside the plates is going to be a different story. We're going to see the field lines start to curve, but we're not ready for that yet. We're going to maintain our position between the two plates so that we have a uniform electric field between the two of them. So what we're going to do now is we will define how much charge is going to be on each plate. We're going to place an equal and opposite amount of charge Q on either plate. And this is actually going to be something that we will see in actual capacitor systems, is that you will have equal and opposite amounts of charge that will deposit onto the surface of these conductors. Now we do need to eventually talk about where that charge is going to come from, but for right now we want to focus on the definition of capacitance. Right now we've defined what a capacitor is. It's two isolated conducting surfaces, but now we need to come up with a definition for capacitance. And we are going to use capital C to represent the term capacitance. And I forgot an N in there. Capacitance. There we go. And capacitance for a capacitor can be measured as the amount of charge that is present on the plates. So Q is the magnitude of the charge value on either plate, divided by the potential difference between the plates. And so we're going to use V as the potential difference measure between those two surfaces. So there's some potential value at the top plate, there's some potential value at the bottom plate. The difference in those two values is what we are going to call V. All right, well, that's a pretty basic definition. It's a ratio. But if you were to go to a hardware store or an electronics store and you want to purchase a capacitor, that capacitor is going to have a rating that is based on its capacitance. So any capacitor, we can think of these capacitors like sponges. They're going to hold onto charge, and there's going to be a maximum amount of charge that any capacitor can hold based on how much electric potential we expose it to. And it's at this point that we're going to start using things like batteries to provide us with the voltage that is associated with a potential difference. And so if you would rather use the term voltage in place of electric potential, that's perfectly fine with me. Just be aware, however, the book may still use the term electric potential from time to time. But what this means is that if I have a capacitor, and this is actually going to be the symbol for a capacitor, we have two parallel plates of equal size, and then we've got these sticks that stick out of the top and the bottom. These are the connection points that we can use for wires in our circuits. But all we want to do right now is connect this capacitor to a battery. And so our capacitor symbol, I'm going to use cap for short. That's our capacitor symbol. For a battery, the symbol for a battery is similar, except that one of the plates is noticeably smaller than the other. And we'll go ahead and use V for potential, or you can call it a battery, that's fine, but the battery is now the source of the potential difference that we're going to use. And if you look at a battery, the battery is going to have a rating on it. It could be a 9 volt, 12 volt, there's lots of different batteries out there. But your battery, let's take something like a C battery or something. You go to the store, you buy this battery. Up here, you typically see a plus sign, and then down here on the other side is a minus. And when you go to plug these batteries into certain electronics, you'll see an opening with a little little spring here, and you usually have the corresponding plus minus so that you know how to hook up the batteries properly. Well, these are just indicating which side of the battery has the more positive electric potential value. For the symbol of the battery, that is implied by the larger plate. The large plate on the battery is the plate that will have the more positive electric potential value. and that is going to be the source of positive charge that comes from the battery. Likewise, the negative end of the battery will be where we have our source of negative charge. So I'm going to go ahead and draw a battery next to the capacitor, and then we'll connect the positive lead of the battery to the top of the capacitor, and we'll connect the negative lead of the battery to the bottom of the capacitor. Now again, the plates of the capacitor are isolated, so there's no connection between the two plates. Yet we have all of this positive charge in the battery that would like nothing more than to leave and spread out, and it can do that over the top plate of that capacitor. And so we would see some positive charge start building up and spreading out over that top plate. Likewise, the negative charge from the battery would love nothing more than to get out and spread out. And so the battery is going to provide us with that negative amount of charge. Now, the battery can only provide as much potential to the capacitor as what the battery is rated for. In other words, if my battery was rated for 12 volts, then the best that I can hope for a potential difference across this capacitor is 12 volts. In fact, because the capacitor is connected across the same 2 points as what the battery lists as a difference of 12 volts, we can now see that the capacitor has a potential difference of 12 volts. So how much charge builds up? Well, the battery is going to provide just as much positive charge as it will negative charge. Otherwise, if it doesn't, that means that the battery is going to be holding on to some excess amount of charge inside, and even though our battery is a source of positive negative charge, we need a net charge of 0 to exist inside the battery, and that means we have to release a net charge of 0. But we now have this separation of positive negative charge between those 2 plates, and those charges are now producing electric field lines. And if we remember from our chapter 22 discussion, those electric field lines are going to point from positive charge to negative charge. All right, well, so we've got our ratio expression here that tells us what the capacitance of the capacitor is, but this is based off of a ratio of charge and potential. Well, I can hook different batteries up to this capacitor. You know, here I've got a 12 volt battery, but there's no reason I couldn't hook up a 9 volt or maybe plug it into a wall socket, which is 120 volts. And so does that mean that the capacitance of a capacitor will change based on the voltage source that I plug it into? And the answer is no. The capacitance of our capacitor is a fixed value. So when you go to the hardware store or the electronics store and you go to buy a capacitor, that capacitor has a certain rating. And the unit for capacitance is going to be a farad. and I've seen it spelled a couple of different ways. Farad without an H. In fact, I think the H is over here, not there. But this second one is the way that I spell it. But we'll use capital F for farad, and that's the unit that we're going to use for capacitance. So you'll go to an electronics store, and they'll have different bins with different capacitors in them. And maybe you buy a capacitor that is rated for 200 microfarads. Okay, that's a fixed value. This is what I call the store-bought value. You go to the store and you buy this specific value of capacitor. That value is never going to change. Yet, we can measure the capacitance as the ratio of charge that deposits on the plates of the capacitor versus the amount of electric potential that we apply to that capacitor. So what this means basically is that if I start connecting stronger and stronger batteries to my capacitor, then that capacitor has to hold more and more charge. So let's see here. How would this work out? Right now we had a 12-volt battery that was hooked up to our capacitor. So let's see what would happen if we have a 200 microfarad capacitor connected to a 12-volt battery. How much charge would be deposited onto that capacitor? Oh, so we just rearrange the algebra. We have 200 10 to the minus 6 times 12. 12 times 200 is going to be, let's see, 2400 10 to the minus 6, or we've got 2400 microcoulombs. Now you can move your decimal around, and you can do your 2.4 10 to the, I guess that'd be minus 3, but as far as the units go, I've got microfarads, and then I just have volts as a standard unit. So my charge is automatically going to come out as a micro for its subscript. So it's just easier to work that way. Well, let's double the potential. Let's disconnect that 12-volt battery and let's hook this capacitor up to a 24-volt battery. What's going to happen then? Well, we've doubled the electric potential, so we're going to double the amount of charge that can be deposited onto that capacitor. Remember, the capacitor is like a sponge. It's going to soak up the charge. Well, think of the water sponge. Does it always have to be completely saturated? In other words, do you always have to get to the point where the sponge is fully loaded and it can't hold any more? And the answer is no. Capacitors work the same way. We don't have to have them completely saturated with charge. The amount of charge that ends up on the capacitor is going to be based off of the physical rating of that capacitor times the value of the potential difference that it is applied to. So really, the capacitance of a capacitor doesn't depend on this ratio. That's kind of weird. We can measure the capacitance by using the ratio of these two values, but the actual capacitance doesn't depend on them. So there has to be some other way that we could solve for the capacitance of our capacitor that doesn't involve plugging it into a battery or measuring the charge that's on it. Maybe there's another way of rewriting this equation using some physical parameters like geometry and um, what the material's made out of or what the capacitor is made out of, etc. So let's see what we can do with this. We already know about charge. We've been talking about charge since day one in class, but we've just recently finished up the chapter on electric potential. So I want to see if maybe we can find a way of rewriting or substituting that electric potential term using some physical parameters of this capacitor. Because when you do go to the store and you buy these capacitors, some of them are going to be big, some of them are going to be small, some of them are going to be made out of different materials, and that's why you have different ratings for those capacitors. So in order to get the capacitance, oops, I'll switch over to my, in order to get the capacitance, I need to know the electric potential between the two surfaces. And we said, well, we can know that if we hook a battery up between the two plates. But like I said, the capacitance should not depend on the battery that you hook it up to. So that's out. I don't want to use a battery value. I need something else that will help me to figure out what that electric potential is. But it's kind of staring us in the face here. We know that when our capacitor plates become charged, they're going to produce an electric field. And we saw in chapter 24 that if we know something about the electric field in a given system, we can use that to derive the electric potential. So here we are in chapter 25. We have to go back to chapter 24 to find the electric potential. But in order to find the electric potential, we have to go back to either chapter 22 or chapter 23 to figure out the electric field that exists between those capacitor plates. So that's where we're going to start. We're going to go back to one of those two chapters, depending on which approach is more beneficial to solving for the electric field. The chapter 22 stuff was the calculus approach. Chapter 23 was using Gauss's law. So we'll need to decide which of those we want to use to find the electric field, and then once we do that, we will start working our way forward again in the physics until we get back to a new and improved capacitance expression. So here we go. Let's move down to the bottom here, and I'll draw another capacitor. So our capacitor will eventually have some amount of charge, equal and opposite charge value, which will start producing an electric field between the two plates. And we need to decide, are we going to use the calculus or the Gauss's law approach to solving for the electric field. And Gauss's law was by far the easier approach in terms of the math, as long as we could find the right kind of container to contain charge. That container was called the Gaussian surface. And what I need is for that surface to exist somewhere where the electric field is uniform. Well, we said that that should be happening anywhere in between the plates. We want to have that uniform electric field. So that's part of my Gaussian surface, but I haven't enclosed any charge yet. And this is going to be kind of difficult if I try to attempt to enclose the entire capacitor somehow. Well, that's not going to work for two reasons. First of all, none of this surface exists in between the plates. But the other reason that that doesn't work is if I try to use this outer container, then I've just contained a net charge of 0, and that's not going to work in Gauss's law. So my only recourse here is that I'm either going to have to enclose the top plate or the bottom plate of the capacitor. That's the only way that I can actually enclose some charge, not have the charge value go to 0, and still have at least a portion of my Gaussian surface actually lying where that electric field is supposed to be uniform. So just to refresh our memories here, Gauss's law relates the charge enclosed by a Gaussian surface to the electric flux that passes through that surface. And we're going to use Gauss's law to help us find the electric field. We need to remove the electric field from the integration. To do that, the first thing we have to do is evaluate the dot product. So how does our electric field compare to the dot product of the infinitesimal surface area? So we're going to go ahead and zoom in. And if you'll remember from our chapter 3 discussions, chapter 23, excuse me, every time our electric field passes through our Gaussian surface, there is an infinitesimal surface area that the electric field passes through. Well, every one of these infinitesimal surface areas is pointing in the same direction as our electric field vectors are pointing. So we have a dot product relationship. Dot products are hiding cosine theta. Theta is the angle measure between the two vectors. Well, everything here is a parallel relationship between the field vectors and the area vectors. Cosine of 0 is 1. And so we're just left with E dot dA. But what about the other surfaces? Well, long story short, those surfaces are not where we are looking for the electric field magnitude. And so one thing that we could do is we could just say, well, we're going to ignore those surfaces. But if we look at the area vector on the sides, how do those area vectors compare to the direction that your fields are pointing? Those are 90-degree relationships, and cosine of 90 is 0. And then when we're outside of the capacitor system, well, you don't just have the electric fields from the positive charges, you also have the electric fields from the negative charges that are passing through that top plate, and those are going to cancel out. So again, long story short, the only part of our container where we actually have field passing through, specifically field that we want to measure, is right in between the two plates of our capacitors. All right, so we've taken care of the dot product. We are assuming that the electric field should be uniform between the plates of our capacitors. So we can bring our electric field outside of the integral. And all that's left is to integrate about the surface that our electric field is passing through. So this is a bit tricky, but I think you'll agree that it makes sense after we see what happens. When you look at the electric fields, where are the electric fields currently running? Well, they're running between the surfaces of the two plates. So, what is the surface area that the electric fields pass through? Well, it's going to be the surface area that the electric fields pass through. Well, how much is that surface area? It's exactly the same as whatever the surface areas of the capacitor plates are. Well, we don't know what the surface area is because we kept saying the shape doesn't matter. And that's still true. But there's no reason that we can't still add up the area of any surface. We're just going to have to give it a generic name like A. A is the area of whatever shape this capacitor happens to be. If it's a circular plate, then we put in the area of a circle. If it's a square plate, we put in the area of a square. If it's a triangle, we can put in the area of a triangle. As long as the two plates have the same shape, so as long as the plates have the same shape, then that surface area of the plates will be the surface area that our electric fields pass through. All right, so there's our expression. We're done with the calculus. So we can rearrange for the electric field. The charge that has been enclosed is the charge of the positive plate, and that is just Q. So that means that our electric field is Q over epsilon naught A. And again, this is a generalized outcome because we don't know for sure what kind of plate shape we're dealing with, but we can always include that in a later step. All right, that's our electric field. So what do we do with it? Well, let's go back up to our roadmap here. So once we get the electric field, we need to use that to find the electric potential between the two plates. Okay, how do we do that? Well, let's go back to chapter 24. In chapter 24, we had an expression that said you can find the difference in electric potential between 2 points in space if you integrate the electric field as you travel between those 2 points. Well, we have 2 points. We want to travel from one plate of the capacitor to the other. So let's bring our capacitor picture up here. We have the positive charges and the negative charges. We have our electric field running between the two. And now it says in order to get the potential difference between the two surfaces, so I want to get the potential difference, I need to integrate the electric field as I travel between the two surfaces. The electric field that we're working with has the magnitude of Q over epsilon naught A. So that will be plugged into the electric field. Let's see here, but let's actually hold off on plugging that in because we've got another dot product here that we need to take care of. And we also have to figure out the direction that ds is going to point, because traveling between these two plates, it sounds pretty straightforward, but really we have to be careful in deciding, do we want to travel from the top plate to the bottom plate, or do we want to travel from the bottom plate to the top plate? And again, it may not sound like it makes a difference, but depending on which direction we travel, ds could end up having an angle relationship of either 0 or 180 degrees. And remember, your dot product is hiding a cosine. So depending on which way I integrate, positive to negative or negative to positive, I could end up getting a positive or a negative outcome from the dot product. Well, again, why does that really matter? Well, it matters because maybe we can use this to our advantage in cleaning up some of the math. Right now, we have a minus sign, which is hanging out in front, and I really don't like minus signs in my proofs. So maybe if I choose to integrate from the negative plate to the positive plate, so I would start at the negative plate and travel up to the positive plate, that would produce a 180 degree difference between my electric field and displacement vectors, which would produce a -1 that I could use to cancel out with the -1 there. And that is so satisfying to get rid of those minus signs. Okay, what's next? Well, I have to integrate the electric field with respect to the displacement, but look at your electric field. The electric field does not depend on the displacement. In other words, the electric field is uniform, just like we were arguing the whole time down here when we actually derived the electric field. If the electric field is uniform, it can come out front. And all that's left is I have to integrate about the displacement from the bottom plate to the top plate. Well, how far is it between those plates? Let's give it a label. Let's say there's a displacement of d between those plates. And that means my integral of ds from one plate to the other is d. You can go ahead and plug in your electric field magnitude. So we have q d epsilon naught over a. That's our potential difference between the two plates. And so what do we do with that? Back up to our roadmap. Now that we know the electric potential, we're going to use that to find the capacitance of this capacitor. And here's that equation that we were using before. C equals Q over V. C equals Q over V. This term right here, this is the potential difference across the capacitor plates. This is the value that is going to be imported into the bottom of that ratio. And you can see what's going to happen. I have Q in the numerator. All of this stuff is going to be placed into the denominator. And right away, we see that the charge factors out. The charge should not be a determining factor as to the value of your capacitor. Everything else, we're dividing by a fraction here, so we have to flip that stuff over. Everything else is geometry and materials property. So compare that to the original ratio that we were using. But now we have epsilon naught A over D. This ratio can be used to measure the capacitance of a capacitor, but it does not define the capacitor. The rating of the capacitor will depend on its geometry. In other words, how large the plates of the capacitor are. So the larger the capacitor plate, the larger the capacitance. It depends on the separation distance between those plates. The larger the separation distance, the smaller the capacitance. But then it also depends on epsilon naught. We've seen epsilon naught in the past. Epsilon naught was often paired together with 4 pi, and it produced our K value. But K was part of a larger construct of geometry and materials property. Epsilon naught was the permittivity constant for air and vacuum, and it told us how these electric properties were going to behave in a medium such as air or vacuum. Well, what do you have? What do you have between your capacitor plates right now? You know, what's in here? Well, I was kind of under the impression that this was empty space. So how do we account for the behavior of empty space in all of our physics 2 problems? Well, we've been incorporating epsilon naught to account for that. And so that's why we see that showing up in this final expression. So this is our store-bought value. This is what I call the store-bought value, because you're going to go to the store, you're going to buy a capacitor, and specifically this is for a parallel plate capacitor, because we specifically used the geometry of 2 parallel plates to put together this combination of terms. But we can always use this ratio to help us measure the value of the capacitor. All right, so now what? What can we do? Well, let's say you've built your capacitor. You have 2 plates. There's nothing in between them, so your epsilon naught says that there's nothing in between the 2 plates. You have an area and you have a separation distance. Well, you hook this capacitor up to a battery of V, and you're able to store a certain amount of charge on that capacitor. Yet that's not enough. You want to be able to store more charge on that capacitor without having to change the battery. Now, as far as this ratio is concerned, that's not possible. You cannot increase one value of the ratio without increasing the other value if you want to maintain a fixed capacitor value. So if I'm going to increase the charge value but keep the potential the same, then algebraically the only way that can happen is if I increase the capacitor value. So how do we do that? Well, we come up here to the physical parameters of the capacitor, and we just kind of ask, what could we do? How could we make that capacitor value larger? And we got a couple of options. Obviously, if I made the cross-sectional area of the plates larger, that would work. If I made the separation distance between the plates smaller, that would work. Or could I change a universal constant? In other words, could I take this empty capacitor and could I put something other than air or vacuum in between the plates? And as long as it's not some kind of conducting material, the answer is yes. You could put some kind of insulating material between the plates, but that insulator is not air, it's not vacuum. And so that means we would have to replace epsilon naught with a new permittivity value. There's going to be a permittivity value that is unique to every material that is out there. And we're gonna talk about this later in the chapter 25 material. This is where we start getting into the topics of dielectrics. So we'll see what happens when we start inserting different materials between the plates of the capacitors, and we'll see how things can change. But this ability to change a capacitor is still kind of limited, because if I want to make a capacitor that holds more charge, one way is to physically make the plates of the capacitor bigger. Well, if you make the plates of the capacitor bigger, then you're spending more money on materials for that capacitor. It's going to cost more money to make larger plates. You're also going to have a larger physical element to your circuit. To physically make the capacitor bigger means it's physically taking up more room, and it might even it's definitely probably going to add more weight to your circuit as well. So that's probably not something you want to do. So we probably don't want to make the capacitor plates any bigger. So how about if we bring the plates closer together? Well, that also carries some risk with it, because if we bring these capacitor plates really close together, then what's going to happen to the charges? If we bring those plates together, what's going to happen is that the material in between the plates, right now it might be air, or could be some kind of insulating material like we talked about. But if we put too much charge on these plates and the potential difference gets too high, then we could see a discharge event where you get charge that will physically leap across that chasm. Remember, these positive and negative charges are attracted to each other by those electrostatic forces. And if we get those charges closer and closer and closer together, those electrostatic forces are just going to get stronger and stronger and stronger until we get some kind of an arc event. And once that happens, your charges mix together and you end up with a null charge. But in addition to that, when those charges arc, there is a tremendous release of energy. And as that energy is transferring from one plate to another, as we're going to find out in the next chapter, there is a phenomenon known as resistance, which generates a lot of heat. And so these discharges of high amounts of charge are going to cause a large amount of heat to be produced, and that heat can quite literally destroy the capacitor. It can melt it. And there's a saying in electrical engineering and circuits, when you see the little blue smoke, it's too late. Or when you smell the blue smoke, it's too late. And so typically with any kind of electrical discharge or fire, the smoke that comes out kind of has a blue haze to it. But yeah, when you smell the smoke or you see the smoke, it's too late. You've already destroyed your capacitor, and so then you have to take it out of your circuit. You have to go back to the store. You have to buy another one, put it back in, and then make sure you don't burn that one out either. So there are definite drawbacks to trying to change the physical dimensions of your capacitor. And nowadays, the best way that we have for making a larger, more stable capacitor is to insert different materials between the plates. And so it keeps the size of the capacitor relatively small, while at the same time preventing any kind of damaging discharge. So it's actually what we call a dielectric breakdown when your material arcs and you destroy your capacitor. But I think that's enough for this video. When we come back, we're going to consider two other types of geometric constructs for our capacitors. We're going to consider a cylindrical capacitor system, which is where you have one charged capacitor nestled inside of another. And because we have two isolated charged surfaces, that will technically constitute as a capacitor. So we want to see what essentially what the store-bought equation for this cylindrical capacitor will look like. And then we'll try the same thing with a system of spheres. We'll have a charged sphere, which is sitting inside of a charged spherical shell. And again, if those surfaces are isolated, we want to see what the store-bought equation for that spherical capacitor will look like. And then we probably only need about 3 videos for this chapter. In the third video, we'll come back and we'll take a look at what happens when we start inserting different materials in between the plates of our capacitors. So, see you at part 2.